So how do we get good performance out of this? Mostly, it's about speed of system calls and traps and up calls. We make those fast. If you have slow system calls, for example, then that tends to encourage complex system calls, right? You want a system call to kind of do a lot so you can amortize its cost. But if the cost is very low, then you can afford to make multiple system calls for things. One other case, so one other example is the trap path doesn't bother saving registers. At least most registers, right? That trap path, that is the code that's being handled in a trap, it may need to use some registers, so it'll save those. We have fast up calls. So we have no need to restore registers. We have protected calls for IPC. So that is, as the kernel, we don't have to get involved in what's being sent. We don't have to buffer anything. All we have to do is just jump to a known address for the yield. So a known entry point, a known up call into the receiving and then back in the sending address. So the fact that we are going directly from one process to another process means there's nothing that needs to be saved. We can do it all with registers. And finally, we're going to map some kernel structures to user space. Most of those are going to be read-only, right? But so at least the application can know what it is without having to make a system call. Simple example, if I had some sort of a data structure of what the free pages are, right, the free physical pages, then I could map that read-only into user space. And so as an application, if I want to know what those are, I just go read the data structure. I don't have to bother making a system call, even if it is a relatively fast system call. So what are the conclusions, really, of this exokernel paper? Well, one, custom abstractions, right? Abstractions specific to a piece of hardware, rather than something that's papering over differences between hardware, are a real win for performance. You need low-level operations for that to work. Much of the kernel can be implemented at user level, right? The amount of work that actually has to be done at a protected level is really very small. And protection doesn't mean a kernel has to implement big abstractions, right? You can protect process pages without managing address spaces, for example. Address space abstraction can be also decomposed, right? We can just decompose it in the exokernel we looked at in terms of what physical pages do you, the application, own, and also what mappings do you have. Since this was published in 1995, there have been a number of calls that have been made to Unix, a number of additions added that add much more low-level control than they used to have. And people also think a lot more about how kernels can be extended. So for instance, there are kernel modules that can be added to Linux, that could be added to Mac OS, and so on. Library operating system kernels are sometimes used. For instance, unikernels are this idea really of you take the kernel and you just compile in your application together. And as long as you have something that just needs one application running, that can go. So an example might be a lot of Docker containers you have out there. Just run one application. You can imagine all of the kernel and that application in a single address space, right? A single protection level.